This paper poses a pertinent question. By way of introduction, the screen shows a portion of the framing of a recently constructed big shed during construction. By way of introduction, I merely pose the question, does this look right, or does the framing look too slender? The term big shed usually refers to ultra-large steel portal frame type structures that are generally built as huge warehouses or distribution centres. Nowadays, big sheds may have a height to eaves of 20 metres or more and cover a plan area of several football pitches. There are a variety of framing systems that may be used, and this relatively light steel framing may be clad with a variety of cladding systems, usually based on thin sheets. There has been a natural evolution from small sheds, small factory premises or farm buildings, to today's big sheds. This evolution seems to have taken place without any corresponding evolution in the design procedures. In other words, structures over 20 metres high are being designed according to standards that were intended for low-rise buildings up to, say, 6 metres high. There are two quite separate design issues that must be faced. The first is the plastic design of unclad frames. In the UK, the portal frame has always been the natural home for plastic theory, and plastically designed portal frames have their own specialist 2D software. And secondly, stress skin design of the clad structures. Stress skin design or diaphragm action was introduced in the context of small sheds at a very early stage. And here we can note that the parasitic or unwanted diaphragm action is always present whether or not the designer wants to take advantage of it. In fact, it can be dangerous to ignore it. However, in the UK, current design of both small sheds and big sheds ignores parasitic diaphragm action. In about 1960, Bryan was involved in the load testing of a substantial small shed clad with corrugated steel sheeting. It was found that the measured stresses and deflections in the frames were considerably smaller than expected. The only explanation was that the cladding was assisting the frames to carry the load. This discovery inspired Bryan into a lifetime of research, investing the interaction between frame structures and their cladding. His immediate aim was to use this interaction to save material in the frames, and so stressed skin design was born. Bryan's early research at the University of Manchester, including the testing of components, the testing of laboratory scale diaphragms, and tests on complete buildings. The outcome was a book, Bryan 1973, that included a complete procedure for the stress skin design of single bay portal frame structures. In 1970, Bryan moved to a chair at the University of Salford, where he was soon joined by Davies, that's me, and the two worked together intensively together to put stress skin diaphragm action onto a sound theoretical footing. Davies brought specialised computer skills that made numerical modelling of the structure cladding interaction possible for the first time. The outcome of some 10 years of research and development was a landmark, the publication of the Manual of Stress Skin Diaphragm Design, a book that brought together all aspects of diaphragm action in framed structures in the UK and European context up to 1982 in a single volume. This defined the state of the art at what turned out to be a turning point in the development of the subject. This book is unique. It has never been superseded. In 1971, Professor Rolf Behrer was invited by the European Convention for Constructional Steelwork, the ECCS, to form a new technical committee with the title Cold Formed Thin Wall Sheet Steel in Building. and Bearer decided that the initial task of ECCS TC17, later renumbered TC7, should be to write a standard for stressed skin design. A preliminary version was published in 1977 with the title European Recommendations for the Stressed Skin Design of Steel Structures. Bearer's preface to this document included the following statements. The committee has taken advantage of the comprehensive experience of the University of Salford in this field of work, in other words, Davies and Bryan, and international specialists were invited to comment on the recommendations. Their viewpoints were greatly appreciated and have largely been taken into account. ECCS continued to work on the subjects of stress skin design and diaphragm action, and the European recommendations for the application of metal sheeting acting as a diaphragm, usually known as the ER, were published by ECCS in 1995. These were strongly influenced by Davies and Bryan, which has been published in the meantime. The ER remained to this day as the definitive European standard for all aspects of diaphragm action. An up-to-date replacement is urgently required. The screens that now follow discuss the calculation of diaphragm action according to the requirements of the ER. The basic shear panel or diaphragm, shown left, is the building block for the calculation of diaphragm action. Individual diaphragms can be tested in the laboratory, as shown right, subject to numerical modelling, as shown centre, extrapolated to full scale and assembled into diaphragm beams and incorporated into 3D models of a complete structure, as shown bottom right. The diagram of the basic shear panel shows optional shear connectors. These were introduced by Bryan in the 1960s to promote stress skin action by providing a direct connection between the cladding and the rafters. This gives rise to the case of diaphragms fastened to the supporting structure on 4 sides. 2 distinct situations may therefore arise in practice. A 4 sides fastened case, where the structure is designed to take full advantage of stress skin action, or a 2 sides fastened case where no stress skin action is envisaged. However, in this case, parasitic stress skin action may still be present and strongly influence the internal load paths through the structure. It is very important to distinguish between these 2 cases, as both may arise in practice and they need to be treated quite differently. There is evidently a need for some clearer terminology here. It's suggested that the term stressed skin design should be reserved for the 4 sides fastened case when the structure is designed to take full advantage of the stressed skin effect. For the 2 sides fastened case and any other situations that may arise where diaphragm action is relevant, the term parasitic diaphragm action should be used, and both of these cases come under the general heading of structure cladding interaction. The ER give a complete family of design equations for the strength and flexibility of individual diaphragms. The detailed derivation of these equations are given in Davies and Bryan 1982. Prior to the publication of Davies and Bryan, there was only one cladding system in general use as the cladding of portal frame sheds, namely a single skin of trapezoidally profiled metal sheeting. By the time of the publication of the ER in 1995, Bearer had introduced cassettes or structural liner trays. Sandwich panels and 2-skin built-up systems were introduced later, and these come with a variety of alternative details. The first overt recognition of the problems caused by the proliferation of cladding systems in a stress skin context came in 1999 with the publication of Stress Skin Action of Modern Steel Roof Systems, a paper by Davies and Lawson. This paper reported a series of tests commissioned by SCI on 6 metre by 6 metre diaphragms with the most common roof systems available at that time. These tests were regarded as indicative of the behaviour, and only limited details of the products tested were published. However, much more detail was archived at the time of the tests and has now been retrieved, so that these tests now have an important place in the development of diaphragm theory. In the meantime, a calculation system for diaphragms with the alternative cladding systems has been set up with the following steps. First, carry out laboratory tests on representative diaphragm configurations. Then develop numerical finite element models for each cladding system. This will require data generators and facilities for extrapolating to full-scale roof planes. Then determine the required properties of each of the components included in the models. And finally, validate the developed models. There is a significant problem with the third step. Prior to 1982, the researchers determined their own component properties as part of their research. With the proliferation of cladding systems, this is no longer feasible, and the onus falls on the manufacturers of the cladding. Recognising this, within Europe, CEN envisages a system of product standards that specify the properties required for the purpose of design. Secondly, the way that these shall be determined, usually either by calculation or testing. And finally, the way that this information shall be presented, for example, by CE marking. The problem is that few such product standards exist at the present time, and those that do may not include the information necessary for the calculation of diaphragm action. The calculation of the 3D behaviour of a clad building is a crucial step in which numerical models of roof slopes are combined with frame models to provide a 3D analysis of the complete structure. The Bryan method was first proposed by Bryan in 1973. At the present time, it is the only method available to designers to calculate the behaviour of a complete clad building. It offers a surprisingly simple calculation that allows the reduction of stresses and deflections in the clad frames to be estimated. However, the Bryan method is only applicable to a structure consisting of a line of identical single-bay flat or pitched roof portal frames running between gables that are assumed to be rigid. It does not allow for a separate degree of freedom at the interface between the cladding and the frames. Therefore, it cannot be applied to the two sides fastened case. Also, it cannot be applied to multi-bay portal frame structures or accommodate any degree of irregularity. It cannot, therefore, be applied to the vast majority of big sheds. Roof pitches have reduced significantly over the years, and nowadays pitches of the order of 5 degrees are normal. Under vertical load there is therefore very little eave spread, and it is this that the cladding attempts to control, so that there is little benefit from structure-cladding interaction. Conversely, in the side wind load case, the cladding is particularly effective in reducing the bending moments and deflections of the frames, but this is rarely critical in low-rise frames. This consideration emerged during the writing of Davies and Bryan, 1982, and this is why research into the stress skin design of portal frames, in other words, Bryan's original intention, came to a halt in the early 1980s. The frames at that time were almost all low-rise, and the potential benefits did not justify the design effort. However, the pre-1982 development of stress skin theory realised the danger of building tall but not the enhanced danger of building tall in a two sides fastened situation, where no consideration is given to parasitic diaphragm action. At this time, research into the two sides fastened case was not pursued to a conclusion, and this presents a problem for contemporary researchers. Consequently, portal frame structures have continued to be designed as bare frames, neglecting any benefits or adverse interactions with the cladding. The technology for the plastic design of portal frames was established by 1981 by Horn and Morris, when, as we have seen, sheds were usually low-rise, say up to about 6 metres height to eaves, and relatively small. The technology in this book gave birth to a new British standard, BS 5950 Part 1 in 1990, and the state of the art has changed little since then. As the frames increase dramatically in scale, the situation that results is much the same as that pertaining to the design of the clad frames, although the reasons are different. The frames have outgrown the available standards. Time constraints mean that we will have to leave this issue without a detailed discussion here, but the news is not good. Round about 2010, problems were first reported in a small number of big sheds in the UK, all clad with sandwich panels. At that time, in the UK, about 50% of big sheds were clad with sandwich panels and about 50% with two-skin built-up systems. The technology of sandwich panels was much the better developed. As well as the ER in 1995, there was a CEN Product Standard, EN 14509, and a significant literature on sandwich panel technology in both English and especially German. However, and significantly, none of this wider literature considered any form of diaphragm action. The typical manifestation of a problem was widespread leakage through the roof that defied the usual snagging procedures, sometimes for several years. Two cases were particularly significant. Both are covered by non-disclosure orders, so that it is not possible to reveal details of the actual buildings or the products used. Building A was a pitched roof portal frame, although it had long roof slopes with intermediate props. The height to eaves was of the order of 15 metres, and it was clad with a common type of sandwich panel with a profiled outer face and a lightly profiled internal face. When the problems came to light, this building proceeded almost immediately into litigation, called by the building owner against most of the parties involved in the design and construction. As most of the parties had both a structural engineer and a cladding expert acting on their behalf, about 20 experts were gathered around the meeting table. There was no agreement regarding the cause of the leakage. The preferred hypothesis was thermal expansion and contraction in the sandwich panels, but no one could offer a rational theory of how this had resulted in the several instances of unexpected damage within the cladding system that had been observed during the forensic investigations on site. After a good deal of debate, a mediation was called involving all the parties. At the conclusion of the mediation, the main contractor accepted full responsibility for the defects, and a large sum of money changed hands. However, this was not the end of the matter, because it was understood that the main contractor would continue the action in order to attempt to recover some or all of his money from other parties in the case. The main contractor then initiated an action against the cladding contractor, who was supported in the case by the cladding manufacturer. Here the issues were more clear-cut, because the main contractor's cladding expert was adamant that the problems were caused by thermal expansion and contraction in the sandwich panels, whereas the team representing the cladding companies believed that the cause was structure cladding interaction. An impasse developed, so the issue went to a binding arbitration. After some forceful cross-examination of the technical issues, the arbitrator retired to consider his verdict. The outcome of this arbitration has never been disclosed. It is probable that litigation then continued without further input from technical experts. Both the cladding manufacturer and the cladding contractor were among those who issued non-disclosure notices to the experts that had acted on their behalf. It is not known what has happened subsequently to the building. This case arose during the course of the litigation over Building A. The building frames were shallow arches and the cladding was sandwich panels with a standing seam detail in the upper face, in order to resist the leakage around the crown of the arch. The height to eaves was again of the order of 15 metres. The initial story was similar to that of Building A in that widespread leakage commenced soon after the completion of construction, and remedial measures continued thereafter for several years. However, in this case, more radical remedial measures were used that probably significantly increased the in-plane stiffness of the roof. The time arrived when the roof was declared to be adequately watertight. It was about this time that a single fracture in a purlin cleat was observed, and the fractured cleat was sent for a specialist technical assessment. The fracture was declared to be a case of fatigue as a consequence of over 20,000 cycles of load. This number of cycles could only be due to wind gusts, and this was a bombshell that changed the landscape. The discussions became more formal and independent cladding experts were recruited. Forensic investigations on site were now systematic and recorded. After this, the situation developed very rapidly as further fatigue fractures started to appear. Remedial measures were proposed and even tried. However, a progressive fatigue failure was accelerating, and further fractures were soon appearing faster than the repairs could be carried out. The building was closed on grounds of safety and for complete re-roofing. At this stage, the independent experts concerned with Building B were dismissed, and non-disclosure orders were issued supported by strongly worded letters by the cladding company's lawyers. All further discussion of this case was conducted behind closed doors. In fact, the actions of the cladding company concerned inhibited all further open discussion of not only buildings A and B, but also other known failures involving sandwich panels. And this included any reference to testing and other research conducted in connection with the cases. Some of those concerned considered this to be unacceptable behaviour, and a small amount of unresourced research continued, based on the fundamental structural mechanics of big sheds, without making overt reference to the forensic evidence, etc., concealed by non-disclosure orders. This research quickly led to the conclusion that any ongoing investigation was going to be dominated by computer software, and that the immediate requirement was for a 3D analysis of a complete clad building that was sufficiently detailed to be able to identify and quantify the potential failure modes. As this research gathered momentum, it soon became apparent that there was a tangible risk of a failure in a big shed due to wind gust loading that could pose a risk to human life. So a report was issued to the Standing Committee on Structural Safety, SCOSS, using its confidential reporting facility. This led to the convening of an ad hoc working group within the Institution of Structural Engineers, chaired by its then president, to consider whether this situation warranted a response by the institution. This group realised that the issues raised went beyond just big sheds. SCOSS have records of other significant failures, with NDOs remaining in place long after the event. NDOs are greatly feared because there are ruthless lawyers waiting to pounce on those who transgress them. And there is a common thread to many of the failures that SCOSS has recently encountered, summarised by the terminology effects of scale. And this recognises that, and here I quote, "The validation of our current design rules has been largely based on years of satisfactory building performance. However, such evidence has been overwhelmingly acquired from smaller scale structures, and so may not be indicative of satisfactory performance in structures of larger scale. This topic is gaining in importance as clients and their designers strive to build lighter, bigger, taller and longer." And so in 2018, SCOSS issued an alert drawing attention to this trend and citing several examples of situations where it has been observed, and one of these examples was the big sheds issue. And from this point, the SCOSS Alert starts to play a major role in the further evolution of the issues with big sheds. Not least, the immediate background to the SCOSS Alert adds an unsavoury political dimension to what is already clearly a major challenge for the construction industry. Evidently, the stability and safety of big sheds was becoming a complex issue. It therefore needed an infrastructure that recognised this political dimension. And so a Centre of Excellence was created at the University of Manchester with the title Structure Cladding Interaction Technology Innovation Centre, SCITIC, headed by Professor Yong Wang. This is intended to provide a forum where issues may be resolved and technical papers published, untainted by vested interests or commercial considerations. At the same time, an off-campus limited company was formed, Structure Cladding Interaction Technology Limited, SCIT, with Professor Mike Davies as its managing director. This company would write and then manage all original computer software developed in connection with the Big Sheds project. And then Michael Roberts, who had been assisting informally in this research, was appointed to a full-time position within SCIT and registered for a University of Manchester PhD with the draft title Numerical Models for Structure Cladding Interaction. A number of technical papers originating within SCIT have now been published, and these are listed in the written version of this presentation. Others are at an advanced stage of preparation. To date, this research has concentrated mainly on detailed 3D analyses of clad frames developed to commercial standards that are capable of identifying and quantifying the potential failure modes that may arise as big sheds increase in scale. Non-linear computer models have been prepared and validated for the most frequently arising framing and cladding systems. This screen shows a numerical model of a simple frame previously tested by Bryan, extrapolated to 3 bays and 9 intermediate frames, that is able to demonstrate aspects of 3D behaviour that have not previously been possible. It shows the distribution of plasticity in the fasteners under increasing vertical load. The finite element model used required over 100,000 nodes, over 30,000 dimensionless nonlinear elements representing fasteners, and over 750,000 orthotropic plate elements representing the cladding. The research to date has been primarily generic In other words, it concentrates on methods of analysis and validation of these methods, leading to a detailed understanding of the phenomena involved. These methods are able to analyse real structures, including, of course, the failed structures. However, SciTech and SCIT are reluctant to publish the results of such analyses until they have received adequate external funding. The stakeholders in SCIT have funded the bulk of the research to date and see no reason why these debts should not be paid off by the beneficiaries. Ultimately, of course, SCIT hopes to be able to provide a much needed service to the industry. The immediate response to the original question, are big sheds safe, has been provided by the failures in buildings A and B. Within the massive building stock embraced by the term big sheds, there are undoubtedly some buildings that are potentially unsafe, but at this time it is not possible to state which they might be, although there are some clues as to what to look for. And it is clear that as sheds become ever taller, the danger increases. It is also clear that within the UK there are chartered engineers in responsible positions who are aware of these dangers but have taken no action. And thank you, ladies and gentlemen, for your attention.